Today's seminar speaker is Professor Maxim Pospelov, and he will talk about the Xenon1T anomaly and theoretical interpretations. So please start.
Well, thank you so much for the invitation. It's a shame that I cannot be there in person. The only time I have visited Korea was under the invitation from Professor Ko, and I attended this meeting at KIOS 7 years ago. This was the most enjoyable time, and I hope at some point in the future we could all repeat the enjoyment. So I'm going to talk today about, maybe it's you should view it as a review talk from my personal perspective, and I've given this talk in a couple of places, so some of you might have heard it already, so apologies if I'll be repeating myself. So I have worked on this topic this year when the anomaly came out, and also some of my earlier papers is relevant for that. So the plan is to talk about xenon-based dark matter experiments, recent experimental excess and its likely experimental causes. Are these axions from the sun? Are these non-trivial properties of light standard model neutrinos? Are these maybe some new dark matter particles that are keV scale in mass or something like that? Or maybe heavier particles with similar mass splitting that gives that type of energy deposition. Or maybe these are some fast particles, some dark radiation or boosted dark matter. And this is basically the plan for the talk. So since I'm going to talk about the topic that I actually been working on and off for a while, going back 12 years ago or so. And I want to acknowledge the contribution by our late friend, Mikhail Voloshin, a faculty in Minnesota, who very unfortunately passed, untimely passed earlier this year. So we've back in 2008 entertained the ideas that some versions of photoelectric absorption of dark matter in direct detection experiments can provide sensitivity to super weak couplings to the standard model, which is superior to all existing indirect constraints. And much of the discussion around this excess is centered around these old ideas. So xenon-based dark matter experiments, well, it is impossible to work in particle phenomenology and avoid hearing about it. This is a very successful scalable technology where the first experiment was really having a relatively small mass of xenon, but adding a mass leads to XENON100 lux, XENON1T, Panda X experiments, which achieve ever increasing sensitivity to direct dark matter detection. The dual phase, sort of the initial scintillation of light due to the sort of molecular vibrations, and followed by the cascade created by ionized electrons in the gaseous phase after they drift the electrons, creates the kind of a two-pronged signal, the signal that can consist of initial scintillation, as I said, subsequent ionization, and they're called S1 and S2, and their relative strength is used to basically select nuclear recoils, but in principle, one can also look at the electron recoil. So this is a cartoon showing the progression from 10 kilograms to 100 kilograms to 1 ton. It all reminds the cartoons where the characters can drink magic potion and become, you know, reaching as ultimate size where you cannot scale it any longer. So this is, of course, not the only scintillation, and for theorists here, the experimentalists know it very well. For theorists here, you can ask the question, why necessarily xenon? Well, there are several answers to this. Of course, the cheapest scintillating liquid that you can have is used in various neutrino experiments. The carbohydrate, the oil-based scintillators are extremely sensitive. But here is for example, a spectrum of a boraxino detector, which is probably the cleanest detector in the world. But the problem is that carbon has unremovable constant the significant background from radiogenic carbon-14, which covers the last 200 keV of energy and cannot be used for the direct dark matter detection, because the energy deposition that you expect from normal models, the most minimal models, is going to be far less. So you are basically instead would like to use other substances, and ideal gases in liquid phase is a good example. So xenon provides scintillation light. Radon, of course, is useless because of radioactivity. Krypton turns out has enough radioactive isotopes. Argon has less isotopes and is cheap, but it's still less radioactivity and is cheap, but still the backgrounds are not insignificant. So, and helium and neon do not scintillate. So that leaves only xenon, which is a fairly expensive material to build the experiments. Nevertheless, it's used around the world now, and quite successfully so. We've seen the basically ever-increasing accuracy and no positive signal for scattering of heavy, weakly interacting massive particles on nuclei, and the sort of the best sensitivity is now below 10 to the minus 46 centimeters squared for a weak scale dark matter, which is quite impressive, and already killed very many models that exist on the market. But today's interest, and I'd say this year interest, is mostly triggered by the studies of electron recoil. So what we should be starting our discussion from is the acknowledging how well this experiment worked. So here is the paper from 2015 with Xenon1T projections, where the collaboration has put sort of their best estimate to what counting rates of backgrounds they can achieve at a low energy over here, if you can see my cursor. And this is at the level of 10⁻⁴ per kilogram per day per keV. And so it's 10⁻⁻⁴ per day per keV, right? Or maybe the level of 30 per year per ton, right? And this is and now you can see what actually has been achieved. That this red curve is the sort of their fiducial model for backgrounds, and this is quite commensurate with what's shown here. So the collaboration has delivered in terms of the low background physics. So this is now the most pure and most precise instrument sensitive to keV scale energy deposition. So this is quite an achievement. So a bit of excitement this year, other than the pandemic, was generated by this excess of events in Xenon1T results, especially in the paper that is entitled like excess of events. And the idea was to look for various soft absorptions of something like solar axions, for example, and see if you can catch that. But so this is how your signal from axions would roughly look like. And so that once they saw this increase, well, you have to call it an excess. This is not the only puzzle in Xenon1T experiment. This is an excess that I observed basically when both signals S1 and S2 are registered. But if you kind of give up on the initial scintillation, if you go to a softer energies of the events and you don't have enough scintillation light from the very beginning, you still can collect ionization electrons, and that's called S2 only analysis. And famously, they have an excess over here, a much larger excess at that relative to what they expect. But they're almost certain that this is not coming from dark matter of any kind of form because of the weird peculiarities I hear from the sort of with timing of these excesses and how they sort of maybe related to switching on and switching off the experiments. So this is just to say that this excess is not the only excess that I observed there. So time stability, time variability of this excess should be investigated. So there were some suggestions that maybe some admixture of radioactive argon seeped through somehow initially, and that this is maybe showing in the timing of the excess. But Xenon collaboration seems to dispute that. What they have acknowledged is the possibility that a low energy, low Q beta emitter might have been inadvertently introduced into the their liquid, only minute amounts are needed. You see by the counting rate here to start sort of increasing the counts at low ionization energies, and in particular tritium have been touted as one of the possible radioactive admixtures that could sort of give a little bit of an increase at low energy here. So of course, all 100 papers that are written by theorists, they're mostly speculations, and these are speculations. What if it's a signal of new physics, right? And this is the so some people have like philosophical differences. A part of the community sort of looks very suspicious to theorists trying to fit the anomalies with their favorite models. But I still think that this is a good, not necessarily a good, but a useful exercise to see what can work and what cannot, and or if size model X works, what kind of other constraints it has to circumvent to be able to be an explanation. And this way we do gain some additional knowledge. Of course, the most tantalizing story of all is that, okay, the sun, the central region, has the temperature approaching 1.5 kilo, KT approaches 1.5 kilo electron volts, right? And so maybe this is a sign of a thermal emission from the sun and absorption inside Xenon. That would be the most exciting, of course. Or this is the sign of non-trivial interactions of light standard model neutrinos. Both these issues were discussed by the Xenon collaboration itself. Or maybe it's a sign of new KV energy scale built into dark matter physics. For example, it could be mass splitting of the two dark matter particles, and the excited state de-excites and kicks off the electron with that kind of kinetic energy. Or it could be a straight out absorption of dark matter, like what we talked about with Michel Voloshin many years ago. Or it could be finally a sign of new, let's call it fast in quotation mark particles, sort of particles that move not with the velocity on the order of 10⁻³ from the velocity of light, but maybe say 10⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻ or maybe it's some sort of a boosted dark matter. And an interesting topic, like what are the maximum fluxes that you can have in this situation? All right, so let me go over basically thermal emission from the sun. This is the most, perhaps, if it works, it would have been the most beautiful explanation. So the solar core has this temperature, as I said. Electrons have, therefore, V over C on the order of 0.1. So this is quite fast, right? So the thermal core of the sun is probed, but very indirectly through neutrino emission and us detecting, well, complicated by the neutrino oscillations, of course, but us detecting the total neutrino flux and electron flux as well. But it would have been absolutely thrilling to see an emission of new weakly interacting particles, very light particles. Imagine that you have, say, an axion-like particle or QCD axion or even a massless particle. If you couple it derivatively to electric field times magnetic field, or you couple it derivatively to the spin of an electron, a thermal emission can occur either through some sort of absorbing a photon and emitting an axion by an electron, or by Primakov conversion of a photon to an axion inside the sun. And so this is, of course, all possible. The question is quantitative. Can we make it work? That is, can we provide a sufficiently large 1 over FA here that would generate the signal for the Xenon1T excess and somehow evade other constraints from the stars? And that is has proven to be exceedingly difficult. Of course, the fluxes of these axions have been calculated very nicely, and like I said, the axion emission is peaking at around, well, depends how you couple, but it cannot be much peaked above the temperature. So typically the emission is peaked at 2 or 3 keV. So this is right where the excess is. Expected axion emission plus absorption inside the xenon atom, it fits the shape of the excess rather well. However, there is also an issue how large the signal can be, and here it's a bit of a disappointment in the sense that the sort of the band where you expect this signal to be explained in the plane of the coupling to an electron and a coupling to a photon is much in conflict to what is allowed by the stellar energy losses. And there's been a number of basically revisits to this story, and each time people look at it, they find even better constraints on G alpha gamma or GAE, and being a factor of say 10 from on the coupling scale here, you can ask the question, well, this is almost infinitely far, right? Because the signal from the sun in this situation scales as the fourth power of the coupling, right? Because it's basically the emission is proportional to a square and absorption is proportional to a square. All right, so that doesn't seem to work for a sort of a bread and butter axion or the massless or nearly massless axion-like particle. It's also difficult or impossible to explain it with the so-called dark photons emitted by the sun. So here is another enviably concise Lagrangian, where to the Stern model we added a new A prime field, new U1 field, which has a kinetic mixing with a standard photon plus perhaps a mass term, right? So if I don't write it, it's probably non-interacting boson, so plus a mass term. And so, as is well known, if the mass goes down, there is a decoupling of the dark photon emission, and in principle, you can get enough of these dark photons to cause enough event rate in xenon. However, the spectral shape of it is shifted much into the infrared, and you would not be able to actually fit the excess. It would prefer to stay flat and have a huge spike at zero. So this is not consistent. Now, the question I'd like or I was asking all the time, is there any models, any model of sub-keV dark sectors or keV or sub-keV dark sectors, meaning the mass here, that could give an excess and evade other bounds? So one can go to a little bit more complicated sort of epicyclical models where you would possibly emit a massive axion that would decay to 2 dark photons, and then the dark photons will cause the ionization of xenon. We, meaning myself and my collaborator from Beijing, Haipeng An, have shown that indeed this model, albeit marginally, can pass the constraints, and we're still thinking of whether we should be writing anything about it. So this is unpublished piece. Another very promising idea, I think, but also sort of marginally consistent, is the solar emission of massive dark photons or axions onto radial bound orbits with subsequent absorption by xenon. This is a beautiful idea by Ken van Tilburg. So imagine you have a keV scale particle that is emitted by a keV scale interior of the sun. So the typical you would produce particles with V over C on the order of 1, and they will just fly away. However, in some rare cases, you'd produce very slow particles that would go out of the sun on the radial trajectory and go back. And so they will, because they're almost non-interacting, they will continue this motion for a very long time unless some sort of gravitational perturbations throw them away from that orbit. If there is such a population, a bit of it can even reach the sort of the radius of the Earth and be absorbed by xenon. And in case of the dark photon, Ken and Robert Lazenby have shown that this, again, marginally, but can be made work, okay, as an explanation. And then, of course, there is a number of papers that is speculating, we can have, some other type of physics. So maybe in vacuum, there is one property to the axion, but once you move to the medium, then it's either mass shifts or a coupling becomes smaller, so that you can sort of put together the stellar energy losses and the Xenon1 tone signal. So this a very strong, excuse me, deja vu for me, reminding the story of 15 years ago with the PV loss anomaly, which all turned out to be not a true anomaly, but this is sort of a last resort models. If one can build a model that evades technical naturalness constraints, then it's great. If not, then why bother? All right, so another class of explanations is based maybe on the neutrino properties. The sun famously is a very strong emitter of the neutrinos, right? So up to 10 to the 11 per centimeter per squared per second neutrinos with sub-MeV energies, this is so-called PP neutrinos, are being generated, and this is a flux at the location of the Earth. So it's tempting to endow, and the xenon signal cannot be induced at that level by the weak interactions of these neutrinos with xenon electronic shells. So in fact, you need a larger detectors such as the Borax-Xenos, no-plus detectors, and so on to study that sort of flux, this type of fluxes. However, what if people speculate the neutrinos have additional properties, perhaps induced by some ultraviolet physics that is not captured by the standard sort of G-Fermi proportional weak interactions. One object of obsession for many people, well, including myself, is that maybe there are sort of electromagnetic moments to neutrinos, and in particular, dipole, electric dipole, or magnetic dipole is sort of nearly massless particles, so it can be either, right? If these are Majorana particles, this could be transitional dipoles between different flavors and so on and whatnot, and that could itself induce ionization in xenon. Thankfully, the flux is very large. But it turns out again that quantitatively it doesn't work all that greatly. And the problem is related again with the stellar physics. If you introduce a magnetic moment to a neutrino, then you will have a possibility of the sort of photon that can be thought of in some loose terms as particle with a mass inside a medium decaying into a pair of neutrinos. So well, of course, in fact, this is the diagrams involving electrons and so on. But anyways, that leads to the draining of energy from the stars, and the current constraints absolutely kill the idea that this is the magnetic moment of a light neutrino, of light standard model neutrino. People have played again with maybe a new Z prime, which would presumably be relatively light, and that would be a new interaction between the neutrinos and the electrons. And you could fit the signal very well, but again, you would have to assume couplings of Z prime at such a level that it would cause problems. You would have to reinvent early cosmology and maybe supernova physics, and just because this light Z primes would have to be all thermally excited, either in early cosmology or during the supernova explosions. And this is maybe one could come up with a more complicated sterile neutrino sector, but I probably won't go into that. So this is cosmology with light and thermalized particles, right? So if you have a new Z prime at a keV and you thermalize it, well, it's a problem, right? Because, for example, early cosmology provides very strong constraints on the abundance of deuterium, on the total energy carried by the light particles expressed as N effective, and so on, and everything, and nothing shows any signs of deviations. And a full thermalized degree of freedom, such as Z prime, which is light, would significantly shift these predictions and lead to the suppression of, say, D over H compared to the observed 2.5 by a factor of a few, which is absolutely not possible. All right, so what do we actually have left? Well, there is a possibility, of course, that it's dark matter that's doing it, right? So dark matter can be there. We can be in large numbers. If it's a keV dark matter, then its abundance can be what? 10 to the 6 per cubic centimeter particles, or 10 to 5 per cubic centimeter. This is very significant. You multiply it by typical velocity, you get a very significant flux, even larger than the standard sort of solar neutrino flux that I was referring to. Maybe this type of dark matter is quasi-stable, not fully stable, but quasi-stable, but can be absorbed by atoms. That's this old idea with Misha that we had. So since then, there's been even before this excess, there's been a number of papers studying for example, dark photons or axion-like particles that are heavy and being sort of eaten by a nucleus, and an electron has been sped out. And so this is the quote from one of these papers, and the dark matter in this range, masses of from 2 to 3 keV, and the so this is a dark photon, right? And the mixing angle below 10 to minus 15 is extremely tiny, right? That can be actually conceivably can be a cause of the excess. But the sort of yeah, and we reached exactly the same conclusion almost simultaneously, like within a day or two from the authors of this paper. So this paper that I've written with hep-ph and Joseph Prowler and Adam Ritz earlier this year. All right. So what are the weak points of that whole story? That the keV scale is just you know, ad hoc in some sense, right? That is, if in the case of the stellar emission, we do have the temperatures of the sun comparable to that mass scale, and therefore the axion emission actually peaks at those temperatures. Here, the scale is put by hand, so to speak, to fit the signal. Okay, could be the case, but you'd hope to see more confirmation for this scale in nature. It could be some other people rightfully commented that it could be actually a heavy dark matter with two subcomponents split by this keV scale, and then the heavy one can be very long-lived, cosmologically long-lived, such as the keV dark matter, for example, and can ionize the atom by bumping into electron, giving it a delta M energy, which is in excess of the binding energy, and causing ionization. So the problem for all these scenarios is that 2 keV, 2 kilo electron volt scale is built in by hand. And well, of course, if you just you know, phrase it in terms of the significance, it leads to lower significance, the signal.
Maxim, I just wonder, maybe there's a constraint from Lyman alpha or phase-space distribution as well, but I just wonder how do people
this is the not the thermally produced guys. If you thermally produce these things, there is not enough thermal production that you can have. So there has to be some sort of inflationary production of this from the initial fluctuations, or just whatever model you would have from the displaced from minimum dark photon.
Is it enough just to decay the producing the dark matter by?
No, it's not a decay. It's an absorption by xenon atom.
Oh.
Yes, this guy decays. If it decays, forget the direct detection. You should look in the sky and look for, it's like for sterile neutrinos, right? Yeah. Sterile neutrinos decay. They produce, if they're I don't know, 10 keV sterile neutrino, well, it produces 5 keV gamma, and looking for that is much more advantageous than to look for your detector where maybe this 5 keV guy will bump into an electron, exchange, do like the charge current exchange, de-excite, and ionize. No, you indeed. Here in the dark photon case, why this is not working for the decay, and that's a good point. I forgot to mention. It's because the decay, there's nowhere to decay to other than the 3 photons. And that happens via the electron loop into a 3 photon. And that's what saves the day, right? So, if you just take an axion that decays to, say, 2 photons straight away, then it's not going to work, in the sense that you would see first the KV signal from an axion, and then you would see the absorption, right, of a generic axion. However, there is a comment here that I put in that ALPS, axion-like particles, so sort of axion-type couplings, but free mass, right, can also work, but there is a problem, right, A to gamma gamma. However, you can make it work if you initially couple this ALP to the axial vector current of an electron. And so when you actually integrate out electrons, you get an additional suppression of the amplitude of maybe MA, which is say a KV, over ME, which is 500 KV squared in amplitude, the square again in the rate. So you can sort of get away with model building, but
I see. Only couples to electron. That's the assumption.
Right, right. And it couples directly to electrons, right?
Oh,
so,
right.
So in both models of this type that survive, for whatever reason, the decay to photons is inhibited. Okay, so that if you can make it, and both of these models pass through these constraints, and everyone knows that now, that then you can make it work, right?
I see.
So this is what I was saying, that people have looked at all these possibilities to see if anything survives all these constraints. Excellent. Yes.
All right. Yeah. Thank you.
Right. One other thing that another class of possibilities is that, well, we may have fast particles around us, right? So we kind of got grudgingly accepted the idea is that there are non-relativistic particles somehow called dark matter, right? There is lots of indication for that. There is no indication for fast dark particles, but they can be there, right? So at a level subdominant, not be seen in the total gravity of these particles, but interactive enough to generate a signal. Okay, and in the last few years, I have actually worked on a couple of ideas that generate fast particles. One idea is that if you have dark matter that interacts with electrons, and let's say it has a small cross-section, 10⁻36 or something like that, centimeters squared, and you send this electron through the interior of the sun, there is like order 1 collision for 10⁻36 centimeters squared cross-section with these solar electrons. And if the collision happens with the interior electrons in the core, and the masses, say, of dark matter particles are close to the mass of the electrons, the recoiling dark matter particles is much faster than the initial V over C of 10⁻3. It can go with the V over C of 0.1. And that can create interesting enough ionization for the xenon type excess. However, it was shown that this gives a too soft a spectrum again. Another possibility is that you can have dark particles that being basically generated somehow by cosmic rays. Cosmic rays can collide with atmospheres. Well, not they do collide with Earth's atmosphere and produce all sorts of mesons. These mesons can decay into fast exotic particles, for example, that later on can interact with xenon and cause an excess or ionization, or it can be existing dark matter particles with sizable cross-section that experience collision with the cosmic rays in the interstellar medium, and that way you create a fast subcomponent to dark matter. And there are many other possibilities in presence. So in a paper with McKean and Raj. We discussed all these different possibilities, and perhaps the largest flux this way of the exotic particles you can get out of this, say, dark matter decay. So if dark matter, 10% of the dark matter can, or a few percent of the dark matter can decay over the cosmological time scale, and if the decays, well, the decays will be happening, continue to be happening now, one can have, so for a GeV scale decaying dark matter, one can have up to 10 to the 4 centimeters squared per second fluxes here on Earth. If proton decays, let's say proton decays to some exotic particles that may interact on the way with a xenon atom, then the fluxes are much smaller. Even though around us we have lots and lots of protons, but but the constraints on the lifetime are much more stringent, and so you get up to 10⁻8 centimeters per second possible fluxes of particles. And so one really exotic possibility that can be sort of entertained is that maybe hydrogen itself is unstable, the atom, not the proton. So there is a class of models with dark particles nearly degenerate with hydrogen, where you can sort of decay there plus a neutrino, and in that case the constraints on a lifetime are not as strong, and you can get fluxes up to the 10 to the 3 per centimeter per squared per second. These are pure speculations, but it's along the lines what is possible, what is not possible. And we have shown that if these daughter particles of such decays, either dark matter or hydrogen decay, if they decay themselves or interact through some magnetic moment, then you can actually feed the xenon excess. Okay, this is very exotic. And then finally, I wanted to sort of last month we've published a paper with Ronnie Harnick, Ryan Plested, and Hari Ramani, and I'd like to maybe spend a few minutes on those. So here is basically the upshot of what we were doing. So we were trying to see if one could use milli-charged particles that would be having a very small electric charge, which is not as unnatural as it may sound at first, be the source of this excess, or in general, can we use low energy sort of probes such as XENON1T sensitive to keV scale deposition to set constraints on milli-charged particles. And we have looked at both possibilities. If the milli-charged particles can be produced by cosmic rays in the atmosphere or in the interstellar medium, that's a minimum production which we'll always have, and or they can be already present at some level in the interstellar medium, and Rutherford type collision with the passing cosmic rays would generate a fast flux. And since the Rutherford scattering is highly enhanced at low velocity, you get very strongly IR enhanced fluxes. If these are milli-charged particles, also they don't fly straight away out of the galaxy, but they're rather curled inside by the magnetic fields, and the retention times are, say, 1,000 times larger due to the magnetic field than just the straight time of the straight passage, which leads to additional enhancement. So if you kind of for particles that are present at 1 part per million, you put this together. This is what their sort of distribution over the velocity would look like. There is a main component that comes from the, you can call it virial dark matter. There is a sort of a medium, much smaller component, but faster component generated by cosmic rays colliding with that spectator particles inside the galaxy. And then there is a fast, you can call it a relativistic flux, generated by cosmic rays hitting interstellar medium or the atmosphere, sort of reacting, producing mesons. So it turns out that this tail is better constrained by experiments such as super Kamiokande, but just because it's much bigger than Xenon1T, it has sensitivity to ionization. If you create a 20 MeV kind of energy electron, you would have to make sure that you don't generate more than 5 to 10 per 20 kiloton per year. Otherwise, you'd be in violation of the bounds that Super K sets. Very well, but this part of the flux can cause a significant part of the events in Xenon, and we have looked at that, and here is our conclusions. So here is the various constraints that one can set on parameter space. So this is like 0.4% of dark matter in this millily charged particles. This is epsilon, roughly the size of the exotic charge. Well, this is 0.001 would be literally milli charged particle, right? And then mk is their mass. So if you go to very small epsilon, you actually have a much better sensitivity through just direct detection. So the virial dark matter is not slowed down. It comes through the overburden, interacts with direct detection experiment, and can be with the nucleus, for example, and can be detected that way. However, there is this fast flux generated by the cosmic rays. The cosmic rays colliding with milli charged particles in the galaxy and creating a fast subcomponent. This subcomponent is capable of inducing ionization, and roughly all these experiments with sort of the lowest bin of the Xenon1T results from this summer, or S2 only analysis from the last summer, they're all roughly have similar sensitivity. If we really want to use that to explain the Xenon1T excess, we might have a problem, because the lower bin, sort of you'd expect, you predict a signal that is still somehow not falling down as steeply as the data suggests, and you overproduce the lowest bin if you want to fit the signal being somewhere along this line. Okay. And so I have reached my conclusion. I have given you some sort of an overview of how I view the field of this exotic ionization being probed by Xenon-style experiments. And there is, I want to emphasize a breakthrough sensitivity to keV scale energy deposition now by Xenon1T experiment. It's the best if you have a model that generates keV scale sensitivity, and this model works in the underground environment, then the Xenon1T signal is, or probe is your thing, right? So it's the most sensitive in that range. Now, strong limits can be imposed on many scenarios, but the excess is tantalizing. I was arguing, perhaps very quickly, that a really light, sort of the canonical axions, or more or less canonical dark photons that are emitted by the sun and absorbed by xenon, do not work in a couple of aspects. It's dark photons do not provide a good shape to the signal, and dark axions would need to have coupling constants in excess what stellar physics allows. Then, of course, one can build ad hoc models, which we did, with dark matter being a KV, or dark matter being split by KV, and de-exciting or being absorbed and creating that ionization. Now, the one thing that kind of I like is that decaying dark matter, or from other sources, can give rise to fast dark matter particles, or dark radiation particles. That can fit the excess as well, and certain interactions, such as, say, milli-charged particles or magnetic moment interactions, they have a certain degree of universality. That is, you give the size of the milli-charge, and the shape of the signal is more or less predicted. And it's not completely clear at this point that that the signal is not explained by that. So it very well may be still that this is somehow some sort of a flux of fast particles that does create an ionization signal. This is all a lot of speculation, theoretical speculations around the rather modest experimental excess. But we will see what the future holds, because there will be more scaled up experiments, even beyond Xenon1T, and we will see. It's so far each iteration of along the Xenon chain has come up with lower and lower and lower backgrounds, and so if that trend continues, the next generation of experiments will have a lot to say whether this is indeed the result of unaccounted backgrounds, or somehow it is by any chance a sign of new physics. Thank you.
Okay. Thank you very much for nice talk. So, question?
Hello, I have a question about a milli-charged particle.
Yeah.
This is just out of my curiosity, but can we see, so the major dark particle is spiraling inside the galaxy, right? And
there can be a situation where there is a small admixture of these milli-charged particles inside the galaxy, yes.
And then can we see, so it should be a synchrotron radiation from this spiraling. It can we, is that observable?
No, not obvious, right? Because synchrotron radiation, you would have to take this particle and scatter it on something, right? And then by itself, it would not emit a photon, because then you'd be iterating this milli-charge a couple of times. So it's a small. I mean, it's all thermalized, right? So it would have to be really fast to generate synchrotron, I would say.
But this is fast, right? 0.1 velocity, is it?
Yeah, sure, yeah. So this is well, this is not enough to generate photons. You can calculate the cross section for leading to photons, and that is a small rate. This is what we're actually using. That these particles are not for it, the universe is the interstellar medium is more or less transparent, right? So you know that if you create a fast electron, it spirals down and stops, right? So it doesn't propagate more than 1 kiloparsec, right? No matter what, because of the magnetic fields and losses due to the synchrotron and Bremsstrahlung and so on, right? But this here there is all that is prorated. It's small because of the milli charge being small. Well, maybe it's too naive, but that's what we neglected these losses.
I see. And I also wanted to ask about is there any impact on the small scale structures with this high velocity within the galaxy scale?
Well, we've taken sort of a very small concentration here, like some percent,
that's a fraction.
right? Because if you start playing with milli-charged particles that do something for you, and you put it, say, 10% of them, right? Then you have such a coupling between the at early times between the baryonic fluid and the dark matter that it will be inconsistent with the CMB. So people have studied that actually quite extensively. Yeah.
I see. So you're taking a small fraction.
So right. So there are lots of unsolved issues, or the issues that are extremely so this topic of milli-charged particles turns out to be far more complicated than you'd naively think, right? So we spend we have spent disproportional amount of time thinking of various issues, and it's its propagation, its accumulation on Earth has not been studied, because this I mean we're going to do that. We're going to publish a paper soon on that, and it's a complicated topic. People have looked at supernova remnants accelerating milli-charged particles, and there is no unity on the conclusions of that analysis either. So it's not an easy going with these particles. Yes. But if you have a sort of a milli-charged flux, this is how your signal, it's more or less universal, I would say, that this is how your signal would look like, right? So depends whether you read much into this lower point. So if you, you know, depends how well the efficiency at this lower band is measured and so on. So it to me it could still be an excess due to the milli charge, right? So the only sort of attractive feature is the universality of the Rutherford scattering, right? So that is attractive. Yes.
Yeah, I see. Yeah, thank you.
Hi, I have another question about milli-charged particle. It just came on me that what happens to the Dirac quantization condition?
Oh, this is when you basically the simplest model is again the same U1 based model, right? So if you have you can probably see it, right?
Yeah. Sure.
Gamma prime diagram
That's
with
right.
a cross in between, right? And this is nothing is wrong with the Dirac quantization. You just introduce a new parameter, this kinetic mixing, and it looks like a milli charge from the point of view of the standard model, right? But then there is something else to reckon with, and that's an existence of so the dark charge can also have its own Dirac quantization
Right,
condition.
right.
So there is nothing wrong with that, right? So I don't think these are contradictory things. So otherwise you'd be able to possibly exclude kinetic mixing this way. No, it's okay.
For example, in the this is just a little bit off the main topic of this your seminar, but for example, the quark is fractionally charged, but we never observe it in isolation because of the confinement.
Right.
But for this milli charged particles, there is no extra confining force that make them.
People play with the confinement with milli charged monopoles and things like that, right? I mean,
I see.
So there are papers if this type of stuff and there is confinement and stuff, right? So there are papers by Chris Verhaeren and John Turning that discuss various aspects of this dark QED monopoles confinement in that sector. Maybe you should have a look. Yeah.
Okay.
So, any other question? Okay. If not, then let's thank the speaker again. Thank you very much.
Well, thank you so much.
Thank you very much.
Thank you.
Yeah. Have a good night.
Good night.
Good night.